This video is the second in a series. We're looking at the relationship between two variables at a time. And in this next case, which is called Charles's law, we're going to look at the relationship between temperature and volume of a gas while holding the other two variables constant. Can you predict the relationship between volume and temperature? Is it direct or inverse? And can you predict or explain why their relationship is direct? So Charles's law looks at the relationship, and again, since it is a direct relationship, when we look back to the graphical analysis that I showed you at the start of the podcast, with a direct relationship, X and Y are written as a ratio, and their relationship is constant, which means as X goes up, so does Y, sort of like a copycat thing. And the slope of the line is the constant. And the slope of the line depends on the things that you have held constant, pressure and number of moles. So you change the number of moles or you change pressure, and then the constant would be different. So that's why we're holding those two things constant, so we do indeed get a line. So when we look at the mathematical relationship, notice that it is different from Boyle's law, which was pressure times volume, situation 1 equals pressure times volume, situation 2. In this case, we have volume over temperature equals volume over temperature. So it's a ratio. And remember that we have to use Kelvin in our temperature, because if not, if we were in Celsius, then we would have positive and negative values and a value of 0, and look at where temperature is found. We don't want negative volumes, we don't want undefined volumes, and so thus we absolutely need to use Kelvin temperature in our calculations. Again, a quick review about converging between Celsius and Kelvin. We have 0 degrees Celsius, 100. Those two things we're familiar with and have been using for a while. Now what we need to do is familiarize ourselves with the conversion to Kelvin. Here is a sample problem. Take the time to pause the podcast, set up the problem, calculate the new volume. What is happening to the gas? Is the temperature increasing or decreasing? Can you predict what will happen to the volume of the gas? And then try to predict why the volume of the gas is changing using the kinetic molecular theory. Again, this podcast is not going to focus on the why. I want you to try to attempt that over the course of this week. 1, be able to do the calculations, but number 2, be able to practice explaining why. Pause it, calculate, and then come back. You should have calculated correctly that as the temperature goes down, the volume goes down as well, remembering to convert Celsius to Kelvin. A third gas law looks at two different variables, this time pressure and temperature. And so as the temperature goes up, so does the pressure. Great example of this are hot car tires or truck tires on a summer day. There are more blowouts because essentially the tire can't expand, and so the pressure builds until it weakens the walls of the tire, and then there's a blowout. So can you perform this calculation? If an aerosol can, not such a good safe situation, can you calculate the new pressure? The answer won't be shown, so I want you to compare your values with others in the class and see if you agree. And then the fourth variable looks at the relationship between volume and number of moles. Well, every time you blow up a balloon, you're adding more molecules of a gas to the balloon. And doesn't that make the volume of a balloon, which has stretchy sides, get bigger? So you can anticipate the equation for Avogadro's hypothesis of volume and number of moles. So what would that equation look like? Volume and number of moles, are they directly related? What does the equation look like? Does it look more like Boyle's law, or does it look more like Charles's law? What does that equation look like? So a practical example of Avogadro's hypothesis is used in a reaction where the reactant and the product are both gases. Remember, you have to do this comparison to be able to compare gases to gases. This wouldn't work for the airbag where you start with a solid and you go to a gas being formed. You have to compare gases to gases. So there are two different gases, oxygen here and water is what we're focusing on. So we have a mole ratio of 7 oxygens to 6 waters. And we have 5.2 liters of ethane. So what it says, what this reaction says, is that for every 2 liters of ethane, 7 liters of oxygen would be needed to react completely with 2 liters of ethane, assuming temperature and pressure are constant. And when they react completely, they will form 4 liters of CO2 and 6 liters of water. And so the Avogadro's equation has been manipulated. As you can see, it was V1 over N1 equals V2 over N2, but then solving for V2 gives you the correct volume of oxygen. And so combining all of these variables together, those that are both direct and inversely related, you come up with an equation that is using all 4 simultaneously. P1 V1 over N1 T1 equals P2 V2 over N2 T2. So, well, how do I remember all of that? Well, there's an easy way. The plane and the vulture fly over the mole and the turtle. What does that mean? The plane, meaning the airplane, which is up in the sky, and the vulture, which is also up in the sky, are above what's on the ground, the turtle and the mole. So if that isn't a way to help you remember how all 4 variables combine, I don't know what is. So to review, we've got 4 different relationships, Boyle's, Gay-Lussac's, Charles, and Avogadro's, where we look at only 2 variables and decide whether the relationship is direct or inverse, and we can graph them. Notice the similarities of 3 of them. And then we have a combined gas law, which is kind of challenging, if not impossible, for us to graph all 4 variables simultaneously. Okay, the combined gas law puts pressure, volume, temperature, and moles, that should be over there, in a relationship. And of course, if moles is constant, then you would simply, if N1 and N2 are the same, wouldn't they mathematically cancel out? And look at what happens here. If you were to erase T1, hold temperature constant as well, look whose law it is. P1 V1 equals P2 V2. Isn't that Boyle's law? And if pressure were held constant, P1 would equal P2, and so you could erase those parts. And then you would have Charles's law, V1 over T1 equals V2 over T2. So really and truly, the plane and the vulture fly over the turtle and the mole can help you with all of these different gas laws, except for the last one, and that is called the ideal gas equation. And the ideal gas equation uses a constant, and that constant symbol is R. Notice we still have the same relationship, pressure times volume over N times T, moles times temperature, equals a constant. In this case, it is a constant that you will either be given or you could look up to calculate a series of problems where there is only one temperature, only one pressure, only one volume given, and you want to calculate the moles. So the other problems, we were given 2 pressures or 2 temperatures or 2 volumes, 2 number of moles, and we had to calculate the other variable. In this type of problem, using the ideal gas equation, we're only given 1 of each. And that's how you recognize the type of problem as well. Given 1 of each of the variables, then you know it's not Boyle's, Charles, Gay-Lussac's, Avogadro's, or the combined, and it is actually an ideal gas equation. So things to remember when you're using the value of R is that you want to be consistent with the units of R. So depending on the units of R given, liter, atmospheres, moles, and Kelvin, if that is the unit, then you would use pressure in atmospheres. If you use a different value of R, then where the pressure is in millimeters of mercury or kilopascals, then you'd want your pressure to be in the appropriately similar units. In every case, though, we want our temperature to be in Kelvin, and we want grams to be converted to moles, which we know how to do, and then also we want volume to be in liters. So it turns out the units of R tell you specifically what units the rest of the problems must have, the rest of the units must have. So there's some applications, and this is the next part of the video that I want you to be able to do. So we can determine one of the four variables given the other. We can look at the relationship between pressure, temperature, and number of moles. And then we can do stoichiometry problems and then gas density. We can come back to the question of why is helium as a gas not very dense versus something like CO2 is more dense. That's the next application. So here is a typical problem. If you look at the information here, it's asked to calculate volume. They give you a mass of a gas. They give you temperature and pressure. Notice that there's only one of each of these things given. So that tells us we need to use the ideal gas equation. It's always helpful to make a list of what you're given, and so that's what's on the next slide. So we make a list, and right away we go, oh yeah, got to go to moles. So we go ahead and make that calculation. We know that what we're trying to find is volume. Since our given temperature in degrees Celsius, immediately convert that to Kelvin. The pressure is given as 101.3. So if we use the value of R that has kilopascals in it, then we don't have to convert the pressure. So that's what I'm going to choose to do. Use the value of R that makes my mathematics simpler. Make this calculation, pause the podcast, come up with an answer, and then go on. How did you do? 22.4 liters. It turns out 1 mole of any gas at STP has a volume of 22.4 liters. Well, what the heck is STP? STP is standard temperature and pressure. 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals, and 0 degrees Celsius, or 273 Kelvin. So if we want to take this knowledge of the ideal gas equation and the fact that the volume of a gas changes with temperature and pressure, then so does the density of a gas change with temperature and pressure. But let's assume that we're under standard conditions, or the conditions of STP. If you remember what density is, mass over volume, we should be able to calculate, since mass is related to moles, and we have the ideal equation that has moles and volume in it, we should be able to calculate the density of gas. In a very simple sense, if we look at Avogadro's idea, and let's say that we have 3 samples of gases, and they're at the same pressure and temperature, and we have the same volume of gases, they do contain the same number of moles. So equal volumes of gases at the same temperature and pressure contain the same number of moles. So if each of these contained 1 mole of helium, 1 mole of CO2, 1 mole of nitrogen, then what would be different? Hopefully you said mass. And if their volumes are the same but their mass is different, what impact will that have on the density? You guessed it, helium is more dense, less dense than the other two. That's why helium balloons float. They're less dense than air. So what you could do to find the density is first find the mass of helium. So let's take 1 liter. What's the mass of 1 liter of helium at STP? Calculate the mass first. I'll calculate the moles, and then go to mass. And then once you have the mass and you have the volume, can't you calculate density? You got it.